I'm going to present a final example of chi-squared testing in action in this video here. We're going to look at homogeneity of proportions, and we have a very interesting example for you. Hopefully this video will help you to think through some of the issues that come up when you're working on this kind of a problem, because, you know, admittedly it can be confusing, and we're not really expecting you to be an expert after a single section in a text, but we're hoping that you know, you can use what you know and think carefully about what you see, and things will become clearer when you do that. So recall, we use homogeneity of proportions when we're trying to find out whether two different populations have the same proportion of individuals with some kind of a characteristic of interest. And it can be difficult to notice when you're supposed to use homogeneity of proportions versus a test for independence if the problem doesn't explicitly ask. And so that's why we're looking at this example here, because it does not explicitly ask. And so you have to kind of think, well, what am I doing here? Let's take a look. The example we're going to be using is number 5. It's visible on the screen in front of you here, and it pertains to Roosevelt versus Landon, as the title says. I don't know if you know anything about this particular situation, but back in 1936, there was a magazine which was known as the Literary Digest. It is a now defunct publication, but at the time it was very, very popular, and they had been doing polling prior to presidential elections, and they had a very good track record. And so people, you know, they had a lot of street cred, let's put it that way. And so when they conducted this poll, it was a very large poll. They sent out something like 10 million invitations, and they received, I think, about 25% of those back. And so they had a huge sample. And, you know, it's a common misconception. People believe that, you know, if you have a huge enough sample, that it's going to cover over, you know, problems with the sample. But the reality is that when you do sampling, when you do polling, you have to keep your eye on both the quantity and the quality. They're both equally important, and so if you miss on either one of those, you can end up with a sample that's not representative, and of course that would create a garbage in, garbage out situation. So anyway, let's read this here. It says, one of the most famous presidential elections from a statistician's point of view is the 1936 contest between the incumbent Franklin Delano Roosevelt, FDR, and the Republican challenger Alf Landon. The notoriety of this election comes from the fact that polling done by the Literary Digest suggested that Landon would win by a 3-2 margin. However, Roosevelt actually crushed Landon in the general election. And so if you're wondering what happened in that particular election, it is very famous. It's very easy to find on the internet. Just go and do a quick search. In a nutshell, the sample, even though it was very large, that was gathered by the Literary Digest was not a representative sample. And so for that reason, their prediction of the outcome of the election was it was exactly wrong. I mean, meaning that what they predicted was the opposite of what actually happened. In any case, let's look at the rest of the problem here. The problem continues in the upper right-hand column here. It says, after the election, author and editor David Lawrence studied the vote. Lawrence asked the following question: to what extent was the campaign a reflection of a new trend in American politics, a trend in which the federal government's paternalistic interest in the citizen brought an amazing reward to the party in power? And so if you read the rest of it, effectively what was going on was the federal government was trying to control the prices of agricultural products. And so they were propping up prices with subsidies. Now, when you read about the subsidies, the amounts of money may not seem like that they're significant, but you have to remember we're talking about 1934 and 1935. And so if you take those amounts of money and you were to adjust them to reflect all the inflation that's taken place since 1934, $100,000 in 1934 is a little bit less than $2 million today. And similarly, $500,000 in 1934 is a little bit less than 10 million of today's dollars. And so we're not talking small money. Even today, if that kind of money was being thrown around at the county level, you know, that's some that's some pretty significant money there, and so that's definitely going to have some kind of an impact. So what we're trying to assess here with this question is, well, how much of an impact? Let's look at the rest of the problem here. You can see that we have a contingency table, and we have rows representing Roosevelt and Landon, and we have columns representing the amount of funding that was provided to the counties in question. Okay, and so you'll notice that there is no marginal distribution here, and so that's one thing that we're going to have to take care of. But let's consider for a second, read part A of the question here. It says, do the data suggest that the level of funding received by counties through the AAA, which was the administration, the agricultural administration under the Roosevelt administration there, do the data suggest that the level of funding received by counties through the AAA is associated with the candidate? So at first glance, you might think to yourself, well, it looks like we're doing a chi-square test for independence. And to be direct, if you fielded the question in that way, you would get most of the credit because, number one, the process is the same, right? We're running the same test effectively, but what we're testing is a different hypothesis. So we would ding you for getting the hypothesis wrong. And if you think through what's going on here, what are we looking at? I mean, what are we thinking about? We are effectively asking if the proportion of individuals voting for Roosevelt is the same as the proportion of individuals voting for Landon or not. And so it is very subtle to recognize that we could be talking about two different populations here. And it might help to know that for many of these types of problems, it is common to think of the voters for different political parties as being from different populations because they have many different characteristics. Even though they may be citizens of the same country, this is one of those kinds of things that tends to divide people. And so it's very legitimate, I think, to consider two populations. In any case, we're going to be entering this into the calculator. And so we want to key in our observed counts and our expected counts. And the matrix that you see, or the contingency table right there that you see on the page in front of you, of course, is your observed counts. And so you could key those in. And if you want to pause the video and follow along on your own calculator, that would certainly be very good. We're going to have to come up with the marginal distribution and the rest of the expected counts. So let's do that. Now please recall, for this particular test, let's look at the inputs again. This is letter C on this calculator's menu, the chi-square test. We are using matrices to hold our observed and expected counts. And so part of the deal, if you're going to use this particular built-in function, is you have to have those matrices with the data contained in them. And so if you recall, in order to get access to those, let's get out of here and let's go back to the matrix menu. And you can see here matrix A and B that are the default matrices for this test. And so if you want to edit those matrices, you have to go to the Edit submenu, and then you can see that matrix A is currently highlighted right there. Number 1 is highlighted. And so when you press enter, you will then be in a position to edit matrix A. Now before we do so, let's take a look again at this. You'll notice here that the contingency table we're working with has 2 rows and a total of 4 columns. Now this one does not contain the marginal distributions, so that will have to be done as part of the problem here. But before we come up with those expected counts, we're going to need those marginal distributions as well. So if you'd like to follow along with your own calculator, feel free. You could pause the video or get this from your text. You want to type in your contingency table as you see it right here into matrix A, and so the size would be 2 by 4. And then you're going to have a similar size matrix 2 by 4 for the expected counts. But before you get those expected counts, you're going to need the marginal distributions. So in other words, the column sums and the row sums from here. And so why don't you join me, go ahead and pause, and you can follow along on your own calculator, and you can see what I end up with on my calculator. So again, we're going to key in our observed counts. So I'm editing matrix A, and if you recall, we said that the size was 2 by 4, and the values would be as follows. And when you're done with that, you just quit from that screen there. You just go second quit. And now you're ready to do your expected counts. But before you do, you're going to need your marginal distributions. So let's take a look at that. You can see right here a key formula that's very important to have when you're doing this. Remember that when you do your expected counts, you calculate it by taking the row total times the column total and then dividing it by the table total for the particular cell in question. And so the first thing you need obviously is the totals. You need the row total and the column total and the table total, and that's what we would typically refer to as the marginal distributions. So let's take a look. Here you can see I've gotten the marginal distributions worked out. And so once I have these, and feel free if you want to pause the video and you can key this into your own calculator, you're going to need to see what we have on the screen right here. But let's get those keyed into the calculator. If you recall, in order to key these in, we have to go to the matrix submenu. And so we're going to be looking at matrix B here. That's where our expected counts are going to go. And the appropriate size would be 2 by 4. And so when you key in those expected counts, you take the column total times the row total and then divide by table total. And so on. And so once you have these keyed in, you should see as follows. So you can see our expected counts here, and again, it may be a good call, pause the video and compare what you have on your calculator screen with what I have on mine here. At this point, we are ready to put down our hypotheses and run the test. Now remember, when you run this particular test for homogeneity of proportions, the null hypothesis, which is always a claim of equality, is that the proportions are equal. And the alternative hypothesis is that at least one of the proportions is different. We don't specify which one. And so if we translate that to something practical for this example, let's go back to the problem and look at it again. Our two populations would be Roosevelt voters and Landon voters, and the proportions we're looking at are from the funding level assigned to each of the counties in question. And so if we translate that to something in writing, here's what we're going to have. Our null hypothesis, once again, is a claim of equality, that the proportion is the same for each of the counties. And so if I write that in sort of a compact form here to get that fit on the screen, here's what I would write. And so then we want to run this test on the calculator to see what the outcome would be. So we were here in the matrix submenu and we'd finished editing our expected counts. So we can quit this and go to the stat menu and go to the test submenu, and we're using the chi-squared test. Observed and expected counts are where we want them, and so really all we have to do is run the test and take note of what we get. And so I'm getting a test statistic of 37.51 and some change, and a p-value which is very, very small, as you can see. And so it looks like we're going to be rejecting. Let's put down what we found. So, as we've said, when we do a hypothesis test and we give a write-up, we always want to have at least the alternative hypothesis. Although in this case, I think, clearly having the null hypothesis is good as well, because it makes it clear that we know, okay, we're doing a test for homogeneity of proportions. And we have our test statistic, and so that's good, because when I see the correct test statistic, it tells me that everything has been keyed in correctly and computed correctly. And then, of course, we have the p-value as well, which we're going to need in order to come to a conclusion. So let's put down our conclusion. Always wise to check and see what the problem was asking before you write down your conclusion. And so it's asking, do the data suggest, in part A here, that the level of funding received by counties through the AAA is associated with the candidate? And our answer would be yes. You can see that our level of significance is 5%, and our p-value is much, much smaller than that. And so we will be rejecting the null. Let's put that down. Now, as far as the practical conclusion is concerned, we can say the same thing a couple of different ways. We can say, in a technical way, that at least one of the proportions was different. We can't tell you which one exactly without doing some additional analysis, but we can tell you that at least one was. And so on a practical level, it shows that, yes, there is an association between the level of funding and the way that the county voted. There may be other factors, but anyway, that's what our test speaks to. Now let's take a quick look at the rest of the problem. Part B is asking that we would construct a conditional distribution of candidate by level of funding. And so if you remember from chapter 4, what that means is that they want us to use the column sums as the denominators and actually look at the proportions in the individual cells. Now, it also says that we should draw a bar graph, but to be direct, we don't require it for this class, because with our graphing calculator, we really don't have any kind of an easy way of coming up with that type of a bar graph. Typically, we would use Microsoft Excel or SS, or like a Minitab or SAS, something like that. But we don't have access to that. We only have a graphing calculator, and it doesn't do that well. So if we want you to have a bar graph, we'll give you one, but we're not going to ask you to produce one, not by hand anyway. Let's just get the conditional distribution very briefly. For our conditional distribution, we need to go back to our marginal distribution, because we're going to be needing the column sums to use as denominators in the calculation. And so I don't know if you want to pause the video and write them down, or how you want to work this, but I'm going to show you effectively what the result would be, and then we can draw the conclusion that they're looking for. So here's our conditional distribution here, and if you're wondering how do we obtain these, well, again, we took the entries in the observed counts and we divided each entry by the respective column total. Be happy to show you on the calculator if you want to see it. But anyway, if you're looking for some kind of an association or a pattern here, you'll notice that the pattern is fairly set. In the counties which received funding, whether it be high, medium, or low, and we do see a little bit of a decreasing trend there. So in other words, the less money they received, the lower the proportion for Roosevelt. We see a pretty clear trend. So for high funding, almost 60% of the voters in that county voted for Roosevelt, whereas about 40% for Landon, and so on. And when we get over to the very far right, where it says no funding or none, you can see that it's almost reversed. So in that case, you have roughly 46.9% of the voters going for Roosevelt and 53% going for Landon. And without getting into deeper demographics, we really can't say much more than that, but that is the conditional distribution that they were asking for. And so if you have any questions about this, feel free to drop me a line. I hope it's helpful.